combinations. The difference is, with a combination than a permutation, we don't actually care about the order in the arrangement. So I guess you could call it a selection rather than an arrangement. So let's investigate. We're going to arrange objects in a line, but the order's not important. So let's just have a look. Well, AB then, as far as we're concerned, is the same as BA. They are the same thing. 5 objects, we're going to arrange 2 of them. If it was a permutation, there's all our possibilities, and of course we know that's 5p2, and yeah, we end up with 20 of them. But if we make it a combination, we've doubled up, because BA is the same as AB, CA is the same as AC, DA is the same as AD, EA is there, and so on and so on. What are we left with? Well, we end up with 10, but it's not just 10. It's the number of arrangements we just had, 20, divided by 2 factorial. The number of ways we could have arranged the 2 objects if that was important to us. So we're, again, dividing out by the number of ways the things could be arranged. Look at another one. 5 objects, arrange 3 of them. Quite a few there. In fact, there's 60 of them. But again, we have some doubling up, because BAC is the same as ABC, which is the same as CAB, which is the same as ACB, which is the same as BCA, which is the same as CBA, and so on, and so on, and so on. And we'll get there eventually. There's quite a few doubling ups. So we got rid of all the doubling up. We've actually ended up with 10, which in this case is the 60 we had, divided by 3 factorial, the number of ways we could have arranged those 3 objects. So to generalise this, if we've got n different objects, and we're going to arrange is possibly a bad way of saying it, but arrange k of them, but we're not concerned about the order, then it would be npk, the number of permutations, divided by k factorial, the number of ways we could have arranged the k objects. So n factorial over n minus k factorial, that was the npk, but now we also have the k factorial on the bottom, and that's quite nice, because if you look at the 2 factorials on the bottom, n minus k and k add together to give n the number on the top. Well, in fact, that's what we call nck, and there actually is a button on your calculator for that as well. I think on most calculators it's on the division key, so nck. But again, just like permutations, it's important we know the formula, because if we're dealing with algebra rather than numbers, we obviously need to be able to manipulate our combination. How many ways can 6 numbers be chosen from 45 numbers? It's the basis of a very popular game that's played every week in the hopes of winning a lot of money. So lotto. So how many different possibilities are there? Well, the order's not important here, because the balls just drop out and you've got to get the same number of balls. So it's 45C6. So that's, wow, that's quite a few, isn't it? 8,145,060 different possibilities. Now, I haven't played it for quite some time, but I think it costs something like 70 cents a game. So if you've got a lazy $5.7 million around, now, you could theoretically buy every possible combination and guarantee yourself winning lotto. It just costs you $5.7 million to do it. Now, of course, what about when it's a big jackpot? You could do that if you had a spare $5.7 million. And you could win maybe the $10 million jackpot. But of course, you're still gambling, because I don't know if you know, but the rules of lotto are, if more than one person gets it, you share the prize. So whilst you might cover every possibility, you're guaranteed of winning it, you can't stop the possibility that someone else will also win it, and you have to divide by the price, so you're probably going to lose money. And let's face it, if you've got a spare $5.7 million around, do you really need to put a entry into lotto? Committees of 5 people are obtained from a group of 7 men, 4 women. How many committees can we form if there's no restrictions? Well, if there's no restrictions, it's just 11C5, because it's just, I'm choosing from 11 people. 5 from 11. The order that I pick them doesn't matter. I'm just getting the committee together. So 462 possible committees. But what about if we go back to the Dark Ages and we say, no, our committee contains only males, which once upon a time they did. Then it would become 7C5. And we cut out a lot of the possibilities. Now there's only 21 possible committees. We could add 462 different ones, but because of our ancient thinking, we only get 21. But then we got enlightened and we said, oh, no, we'll let at least one woman be on the committee. So how many contains at least one? Well, we can still use our complementary idea. So I can say, well, I know there's 462 in total. If I take away those 21 which don't have any women in it, I must be left with the number of committees that are only one. So 441. 5 cards from a regular pack of 52. How many different hands could be dealt out? So there's 52 cards. We're going to deal out 5 of them. The actual order that they're dealt doesn't matter, because if you are a polite card player, you don't pick your cards up until they're fully dealt. You don't pick them up one at a time. That's very poor form when you're playing cards. There we go. We have 2,598,960 different hands of cards that we could get. So what's the probability of getting 3 of a kind? The first thing I'm going to do is work out which number is going to be 3 of a kind. So that's my first choice. There are 13 different, numbers, if you consider Jack, Queen, King being numbers. And I've got to choose one of them to be the 3 of a kind. So 13C1. Haven't got any cards yet, but now I know I need to get 3 of them. So of the 4 of that number, I need to choose 3 of them. But I need 2 other cards. There's 48 cards left, 48C2, 58,656, which actually, when you think about it, is not correct, because what have I done here? Anyone play poker, know the rules of the games? You see, 48C2, I could get a pair of another numbers now, and I'd have what's called a full house. And a full house is not 3 of a kind. So technically, I should have subtracted the ones that are a full house. But as I say, we don't need to know all the rules of the poker hands and what have you.
Wouldn't it be 49 for the 40?
No, because if I go 49C2, now I could get 4 of a kind. So I had to discount the other one that I didn't pick. Yeah. Therefore, the probability of being dealt 3 of a kind is around about 3.2% chance of getting 3 of a kind. In fact, that's how they work out which hand beats another hand. It's all based on the probability of getting it. Let's look at an actual HSC one, albeit quite old. A 4-person team's being chosen at random from 9 women, 7 men. How many ways can we choose this team? Well, again, the 9 men, 7 women doesn't matter. We've got 16 people. 16C4, 1,820. Part 2 then said, well, what's the probability that the team will consist of 4 women? So from the 9, we're going to choose 4, 126. But they've asked for the probability, so let's put it together. 126 out of 1,820. There's a 9 in 130 chance of that happening. Going to look at some shortcuts that can help. Because a common question in this stuff is dividing into groups, getting objects and putting them into groups. So this case here, I've got m plus n, whatever m plus n is. That's how many objects, and I'm going to divide them into 2 groups. One group has m objects, another group has n objects. So the number of selections would be, well, I've got m plus n all up, and I'm going to choose m to place in a group. Now that automatically means the ones I haven't used become another group, so I don't have to do anything else. So it's just m plus ncm. In factorial notation, it's m plus n factorial over m factorial n factorial, which is quite interesting when you look at it. Because on the top, we've got a total number of ways of arranging m plus n over the group of m, number of ways of arranging them, and the group of n. There's another way of thinking about it. Even though it's a combination, I can use the factorials to get my answer. Why is that idea important? We'll see in a little while. What about if the groups have the same amount in them? So I've got 2 m objects, and I'm going to divide them into 2 groups that both got m. So it'll be 2m, and I'll choose m of them. That automatically creates the other group. But in this case, I have to divide by 2 factorial. Got to do that. The reason why? Well, okay, let's say they're groups of 4. I've chosen one group of 4 over here. This automatically became the other group of 4. Okay? But I could have just as easily chosen this group over here, and then they became the other group of 4. So you've double counted the possibilities. So if the group size is the same, you divide by the number of ways you could arrange those groups of the same size. So in this case, divide by 2 factorial. So it would end up being 2m factorial, n factorial, the 2 groups, but then also 2 factorial, the number of ways we could have arranged the 2 groups. Let's take it a step further. I now have m plus n plus p objects. I'm going to divide them into, it says 2 groups, but it should be 3, shouldn't it? Into 3 groups of m objects, n objects, and p objects. What would this be? Okay, first of all, I would choose my group of m objects. So that would be m plus n plus p, cm. That would leave me with n plus p objects. So now from those n plus p, I'm going to choose n objects to become the second group, and then that automatically leaves me the p objects for the third group. But look what happens when you play around with the factorials. You see the first one becomes m plus n plus p factorial over m factorial, n plus p factorial. The second one, n plus p factorial over n factorial p factorial. The n plus p factorials cancel, and look what you end up with. It's still the same idea as when we had 2 groups. Total number of all of them divided by the size of the groups. M factorial, n factorial, p factorial. So we can save ourselves some time when we're dealing with groups. Which is total number factorial over the size of the groups factorial. Well, here's m, n and p are the same size, but in how many ways can 15 students be divided into 3 equal groups? Then I would say 15 factorial, size of the groups, 5 factorial, 5 factorial, 5 factorial, but I will also divide by 3 factorial the number of ways I could arrange the 3 similar sized groups. Now, if 2 of the 3 were the same size, let's say we had for this one 6, 6 and 3, then I would go 6 factorial, 6 factorial, 3 factorial, but I'd go 2 factorial because only 2 of them are of the same size. So we divide by 3 as 3 groups are of the same size. We go to a restaurant. The restaurant's got 3 tables. Each of them have got 4 seats. 12 people arrive for dinner. How many ways can they be assigned to the tables? Here's a subtle difference, because what I would do is this. Well, there's 12 people. I'm going to arrange them in 3 groups of 4. So 4 factorial, 4 factorial, 4 factorial, but then 3 factorial. However, now I'm going to go and do something with these groups, because now I say multiply by 3 factorial, because how many ways could I now organise these groups onto 3 tables? So effectively, I didn't need to divide by the 3 factorial. So if you're just forming groups, you divide it. But if you're then going to use them to do something which will make them distinctly different, it might be 2 groups and you're going to play a game of basketball or something like that. So team A, this over here, well, you lost a player, bad luck, they've been sent off. There's team A and there's team B. That actually is different to them being team A and them being team B. So you don't divide by the 2 factorial in that case, because they will be wearing different jerseys or whatever. If you're going to use the group and actually place them somewhere, then you don't have to do that. A permutation is actually a combination. It's always weird we do permutations first. When you think about it, a permutation is actually a combination that we get the combination, but then we multiply it by the number of ways we could arrange the groups and that idea. So some people think of a permutation as select, then arrange. Now, there's this idea insertion method. This is really useful when some objects are not allowed to be together. This is probably more back on permutations now rather than combinations. So we've seen questions like this. The letter of the word between, ranged in a line. How many ways can they be arranged if all the E's are separated? The traditional way of doing it you would look after your restrictions first. So the first thing I want to work out is how many ways could I place these E's so that they are separated. So I've got this many letters. I could put the E's in that position there. And they're all separated. Well, actually, that last letter could also go in the second last spot and they'd be separated. And actually, that last letter could go in the last spot and they'd all be separated. So there's three ways if E's take the first and the third spot. But what about if the E's take the first and the fourth spot? Then I could place the E in the second last spot, but I could also place that last one in the last spot, and that gives me another two ways I could place the E's. But that's if I put them in the first and the fourth spot. What about if I put them in the first and the fifth spot? Then the other E, there's only one spot it could go, and that's at the end. Okay, I think I've used up every possibility where the E goes in the first spot. But what about if I put it in the second and the fourth spot, and then I could put it in the sixth spot, but I could also put the last one in the seventh spot. That's two ways. But what about if I put it in the second and the fifth spot, and then it could go in the last spot? So that gives me another one way. I think we've used up all the ones where the first E is in the second spot. But what about if I put the first E in the third spot, then the next one could go in the fifth spot, the next one goes in the seventh, and that's about it for that one. And I think that's all of them. So there are 10 ways I could place the E's. This would be the traditional way of doing the question. So I'd say, well, it's 10, and now I'll arrange all the other letters, 4 factorial, and I come up with the answer. Okay. We're going to do the insertion method by actually thinking about this backwards and where we actually look after the restrictions last. So we're going to place the unrestricted objects first. I could have put them that way. But you see, what happens is we create spaces to place the E's. And because none of the E's can be next to each other, I can only use 3 of those 5 spaces. I have to now choose which 3 spaces. So it'll be times 5C3, and there's my answer, 240. A heck of a lot quicker. What about if I said exactly 2 of the E's are together? All right, same idea. 4 factorial for those letters. I have these spaces. 2 of the E's are together. So it now means like I'm going to place 2 objects. One of those objects is a double E and the other is a single E. So I'm going to put 2 objects in these 5 spaces. But now, because the objects are different, the order becomes important. So we multiply by 5P2 rather than 5C2. And there's our answer, 480. That's what we call the insertion method, and actually can solve some of these problems quicker. The idea of using what we call separators. This is really good when we want to divide big groups into smaller groups. Here's a question that I wrote for one of our trial HSCs one year, I remember. I thought it was a great question myself. I'm not biased though. 3 pirates are sharing out the contents of a treasure chest. Although if it's a pirate, they wouldn't say a treasure chest, of course. They'd say a treasure chest. Because you roll the R's if you're a pirate. Got my treasure. It contains 48 gold coins and 2 lead coins. The first pirate comes along and they say, righto, pick out as many coins as you like, but as soon as you pull out a lead coin, that's it. That's your lot. So you might get lucky and pick out all the gold ones, but you might get unlucky and pull out a lead one first. They're the rules of the game. So once the first pirate's taken his treasure, the second pirate comes along, same rules. Okay? Keep pulling out until you get a lead coin. And then the third pirate gets whatever's left. How many ways can we distribute the coins? How many ways can we distribute the coins? So if you think about it, let's convert this problem into a more familiar problem. Instead of coins, let's call them letters. And those letters are going to be L and G. So how many ways can 2 L's and 48 G's be arranged in a line? Because when I've got them in a line, is that any different to a pirate coming along and picking the first one, then the next one, then the next one, next one, and the next one? So the 2 L's are acting as what we call separators between the pirate's treasure. Well, we know how to do that problem. 58 letters, so 50 factorial over 48 factorial, 2 factorial, 1,225 ways those coins can be distributed. I use that example because it now brings up actually an extension 2 question. There used to be a topic in extension 2 called harder extension 1. It was a great topic because you could pretty much ask anything you like. Permutation combinations was always a favourite. Unfortunately, not there anymore. But anyway, let's look at this question. How many ways can 10 identical coins be allocated to 4 different boxes? Now, it's essentially the exact same question as before, different numbers, of course. Because I could say, how many ways can I arrange 3 S's and 10 C's? 10 C's are the coins, the 3 S's are the separators. Because we will arrange them in a line. It's no different to saying that first group, you're going in the first box. That second group, you're going in the second box, and so on. So it's really an identical type question. Well, there's 13 all up. 13 factorial over 3 factorial, 10 factorial, which gives us 286 ways of doing it. The interesting thing about this question, when they asked it in extension 2, 1% of the state got it correct.
So it's 1% of extension 2.
Of extension 2. 1% of extension 2. It's usually around about 3,000 people do extension 2. So you work it out. 1% of 3,000, about 30 people got it. Let's try this one then. Also from extension 2. A hostel has 4 vacant rooms. Each room can accommodate a maximum of 4 people. In how many ways can 6 people be accommodated in the 4 rooms? Right, well, if there were no restrictions, there would be 4 to the power of 6 ways. Because the first person could come along and say, oh, I'm going to choose that room. They've got 4 choices. Second person would come along, I'm going to choose that one. They've got 4 choices. All 6 of them would have 4 choices. So 4 to the power of 6. You see, I'm going to use the complementary idea and take away the possibilities that we don't have. So we're not allowed to have all 6 going into one room. Let's work out how many ways that is. All 6 would have to choose the same room. So we basically just got to choose the room, 4C1. And that's the room they're all going into. Okay, so we're going to subtract 4. But the other thing we can't have is 5 in a room. Now, if there's 5 in a room, what that means is 5 will go into one room. So let's choose that room, 4C1. We will now choose which 5 people will go in that room, 6C5. One person left over, they got 3 rooms to choose from, 3C1. 72. We do a subtraction and we come up with 4,020. They did a bit better than the other one. 15% of the state got it correct. Until you realise one thing. It was a multiple choice question. Think about it. You got a 25% chance of guessing it correct. 15% got the right answer. So, look, I don't know. Is it a good thing or a bad thing? It's no longer an extension 2 and you don't get these really hard ones. I personally think it's a bad thing because they're great fun, but you know. Alrighty, that'll do us.